Okay, so last section of this long unit that we've been talking about probability. So the last thing we're going to talk about is the extension of what we talked about last time, permutations. Now remember, permutations were an arrangement of objects, and the thing that matters is the order. Okay, so particular orders matter. There is either a ranking or a preference or a hierarchy or something to that effect. So the alternative is something called a combination. And with a combination is an arrangement of objects in which order is unimportant. So I want to illustrate the difference because I understand that, again, you're learning a whole bunch of stuff about probability and all this, so it can be a lot to take in. So for instance, let's just review real quick what we talked about last time. What we're going to do is we're going to consider the set A, B, C, D. So we've got four letters, and what we're going to do is we're going to list all the permutations. Okay, we're going to list all the different ordered arrangements. Okay, so for instance, if order matters, all the permutations of two letters. If order matters, then AB is different than BA, right? Those would be different arrangements of objects. Order matters. And so I'm just going to list out all the others, and then I'm going to show you the difference between the permutation where order matters and a combination where order doesn't. So we've got AB and BA, and then we'll have another pair, AC and CA. Those would be different things. Then AD and DA, those are different things. And then that's everything I can do with the letter A. So now with B, I've got BC and CB. And then I've got BD and DB. And finally, I've got one more pair of letters that I can consider the different orders. I've got CD and DC. Okay, those are all the different arrangements of two letters out of those four. The other thing we talked about last time, again, this part is just real quick overview of last time. We can talk about how to calculate how many different arrangements. So we've got here that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the way we can calculate that is we had the permutation formula. I told you that when order is important, we can use our calculators, and this is the formula. We got the permutations of four objects. I've got four letters, and I'm taking them two at a time. And this is all in your notes. You don't have to write this if you don't want to. This is not a particularly large number or complicated example. And so in the numerator of the permutation formula, I've got 4 factorial. That is the permutations if I use all four objects, 4 times 3 times 2 times 1. But we're not using all 4. We're only using 2. So that means we're leaving out 2. So, oh, the exclamation point, that is called the factorial. And what the factorial means, I'm just going to slide up. So when you watch the video for section 11.7, I explain this, but I'll review it real quick here. The exclamation point is a mathematical object, and it's telling you you're going to start at the number 4, and then you multiply 4 times 3 times 2 times 1. Okay, it means multiply every number down to 1. So if I had 6 factorial means 6 times 5 times 4. Yeah, it gets pretty boring pretty quick. I get you. Okay, so that's what the factorial means. Okay, and then when we do that, you can pop that into your calculator. If you don't know, again, I mentioned this, I think almost all of you were here last time. If you don't know where that is in your calculator, I can help you with that, but that's going to give you 12. Sure. All the way down to 1. So like 6 factorial, we started at 6 all the way down to 1. If we had 20 factorial, it would start at 20 all the way down to 1 and be a long string of numbers. Okay, so for those of you who just walked in, we're at the top of the page. I basically just spent a few minutes reviewing the idea of a permutation, something where order matters, and we listed out all the permutations when I grabbed 2 letters out of these 4. Okay, so there's 12 different permutations, 12 different arrangements where the order matters. Now what we're going to do with that same set of 4 letters, we're going to list the combinations. Combinations mean I just care about the group. I do not care about the order. Okay, so so in this case, AB and BA, okay, we would consider that one. We would just say, I'm just going to put A, then B. I'm just going alphabetical, but those two things here, if I'm considering combinations, AB and BA would be equivalent. And so it's just a matter of having A and B. And the same thing here. These two things would be equivalent, okay, in combinations. So all we would have is A and C. And then here, AD, DA, those two things would be equivalent. They mean the same thing if I don't care about order. BC and CB, again, those would be the same thing. And I can do this two more times. I have BD and DB, and then CD and DC. What I've circled means the exact same thing if I'm talking about combinations, areas where order does not matter. So what we can do is we can extend the permutation formula. We can come up with what's called the combination formula to determine how many. So in this case, when I have 4 objects, I'm choosing 2. Order doesn't matter. There were 6. Okay, there's 6 combinations. And so here's the combination formula. This time, when you determine, again, when you did your homework for 11.7, I said one of the big things that I asked you to do was to make sure you understood in each situation why order was important. And that way, when you go and do your homework in 11.8, you can ask yourself the alternative question. Why is order not important in this problem? Why am I just concerned with the group? And so when you identify that order is not important, you're going to use the letter C. C stands for combination. Then over here, I put the number of objects, just like we did with the permutation formula last time. And here I use how many I'm using. So I'm going to label these things. Okay, N, this is the total number of objects. R is how many I'm using. And I'm going to give you a second to get caught up, then I'm going to write out the combination formula. It's super similar. If you remember the permutation formula from last time, we're just going to add one thing to it. Okay, so it builds on what we talked about last time, and so hopefully it makes it a little easier to remember. So here it is. This is the exact way we started out last time. Starts out with n factorial up at the top. And remember, n factorial, this is the number of ordered arrangements of all objects. Then we're going to divide that. I'm sorry, I'm not meaning to make a big mess of this. I'm just trying to explain each individual term, hopefully to help make it a little more memorable. So then last time, remember with permutations, we divided by n minus r factorial. And that was the arrangements of the things we're not using. Okay, so let me write this in a different color. So this is the arrangements of objects not used. If you can't read that, it says not used. So n minus r factorial is the arrangements of the objects that are not being used. So far, that's the permutation formula. Okay, that's the number of ordered arrangements of the objects. So in my example, using this gave me 12, and we can count them right here. So what we have to do to indicate that order doesn't matter is now we're going to divide by this r factorial, and that's the duplicates. So by dividing by that, I'm saying, okay, A, B, and BA, those are the same thing. It's just a group that has A and B. And AC and CA, that's just a group that has the letters A and C. And so order does not matter. All right, so the rest of our time together is just going to be practicing this and just making sure we see how we can identify that order doesn't matter. Remember when we did the permutations last time, order matters when there's some sort of ranking or hierarchy or preference when something coming first and second makes a difference. Okay, so that was, we had an example where we're picking a president, a vice president, and a secretary for a club. Okay, if you got picked first, you were going to be something different. You're going to be president. Okay, if you got picked second, vice president, order mattered. Or we did a leaderboard. How many different ways to arrange people on a leaderboard? Well, a leaderboard, first, second, third, it matters where you end up. Okay, so that's going to be opposed with what we talked about today. So here we go. Example one, I'll do this one with you, and then I'm going to let you practice. So it says, in a class you're taking, you're assigned to read any 3 books from a list of 8. So there's no, you're going to get more points for the first one. There's no ranking. There's no hierarchy. You're just picking any 3 books. Okay. And how many ways can you select the 3 books? Okay. Well, since order doesn't matter, there's no indication here that there's a preference. This is a combination problem. How many objects do I have to choose from? 8. How many objects am I choosing? 3. Okay, remember, this is what I require on the test. This first step tells me that you know it's a combination. Order doesn't matter. The second step is you're going to pop it into that formula. So I've got 8 factorial. That's the number of arrangements of all 8 objects if I listed them all out. But I'm not using all 8. I'm only picking 3, so that means I'm leaving out 5, or 8 minus 3. That's the number I'm leaving out. And then since order doesn't matter, we're getting rid of the duplicates. So 3 factorial, getting rid of the duplicates. Now, if you got a scientific calculator, your scientific calculator should do this. Okay, it's in the same menu as I showed y'all last time. If you don't know where that menu is on your calculator, wave your hand. I'll come around to you. I don't have my calculator. It disappeared on me, so I'm going to have to do this out the long method. So either way, we should come up with the same answer. So this is 8 factorial divided by 5 factorial and 3. So I showed you this last time in case you don't have a calculator that has this. So what I'm going to do is I'm going to take 8 factorial. I'm going to go 8 times 7 times 6, and then the 5 times 4 times 3 times 2 times 1. I'm not going to write out. I'm just going to write 5 factorial. And the reason I do that is because I have a 5 factorial in the denominator. They're going to cancel with each other. I don't need to do any extra writing there. The 3 factorial, I'm just going to extend to 3 times 2 times 1. And now everything should cancel. I should get a whole number at the end. There should be no fractions at all. So 5 factorial and the 5 factorial, those cancel with each other. 3 goes into 6 and leaves 2. 2 goes into 8 and leaves 4. And so I'm left with 4 times 7 times 2. 4 times 7 is 28. 28 times 2 is 56. So however you do that with your calculator, if you have the buttons, make sure that you got 56. If you don't have the buttons, make sure that you're able to do the arithmetic. Okay, so most of my calculators I have for you when you borrow them will have it. Also, my calculators that I have the exclamation point. So you can do, if you don't have this button on your calculator, if you just have the exclamation point, then you can do 8 factorial and then divide by 5. You can do it that way. Question? I could have done that too. Yeah, it wouldn't have mattered. Yeah, if I canceled this 2 with that 2, then I would have 8 times 7, 56. Yeah, it would have been the same thing either way. Great question. Yeah.
I'm kind of confused about the duplicates. Like, how do you
This is the value of R. What it is I'm picking 3 objects. So this 3 factorial says I'm dividing out all the duplicates of those 3 things. Okay, so that's why that's 3. This, the 5 factorial, the 8 minus 3, that is all the arrangements of the stuff I'm not using. I'm just getting rid of all the stuff I'm not using. And then this is, I'm getting rid of the duplicates now. Okay. Great question. Glad you're processing it. We'll do some more processing. Try example 2. You're helping ice cream shop determine how they can advertise how many different types of banana splits that they can have. And if you need any help with your calculator, raise your hand. That's totally fine. I'm coming to you. I'll give you another minute to get the numbers plugged in and see what your result comes out to be. Okay, so it says an ice cream parlor has 20 different flavors. Cynthia orders a banana split and has to select 3. So again, there's no, you're not getting more of the first and less of the second. So there's no difference in what order you pick these 3 flavors. That's why order does not matter here. So how many different selections are possible? So it's a combination problem. How many objects do I have to pick? I have 20 total objects and I'm picking 3. Great job. So the formula is 20 factorial. Again, that is the ordered arrangement. If I pick all 20, I'm ordering all 20, but I'm not using all 20. First of all, I'm only using 3. So that means I'm leaving out 20 minus 3 or 17 of them. So that is, remember, that is I'm dividing out all of the ones I'm not using. And then since order doesn't matter, okay, this is the new bit for the day, I'm dividing out the duplicates of those 3. So it doesn't matter if I pick chocolate, then vanilla, then strawberry, or strawberry, then chocolate, then vanilla, it's the same bowl of ice cream. And so then I'm going to use I'm going to ask you, what did you get when you used your calculator on this? 1,140 different ways to do that, yes. So that ice cream shop can, and you see this when you go around to businesses, if you ever see a business that says there's this many possibilities, they've just done something like this. Like if you go to, if you ever gone to Firehouse and they have the Coke machine, and the Coke machine up at the top in the corner, it says that there's, 8,000 different beverages you can get. They've just done a combination problem on the beverages to make it seem like it's more than it is. Okay, so this is a simplified version of something that's actually used. Okay, try the next one. We're just practicing. Example 3, please. Okay, so Paul has 9 CDs. He wants to select 4. Again, he's not picking his favorite and his second favorite. He's just grabbing 4. Got to update the example because no one uses CDs anymore anyway. So I got to get modern. And how many ways can he select 4 out of the 9? So combinations. There's no inherent order that I've been asked about. Paul has 9 total CDs he wants to choose from, and he is picking 4 to take with him on his road trip. Okay, so here we go. So it's 9 factorial. That's the ordered arrangements if I'm using all 9. But Paul's not using all 9. He's only using 4. So that means he's leaving 5 of them home. Okay, or 9 minus 4. He's leaving 5 of them. And then we're getting out all the duplicate arrangements because order doesn't matter. And so again, you can go ahead and do this the longhand way. And if you need help with the longhand way, just see me after class. It'll take us 35 seconds to go through an example together. But when you throw this into your calculator, what does it end up being? 126. Thank you very much. There we go. That's the essence of combinations. So I've got one more thing we're going to do with the combinations. We're just going to tie it together with something we've already done, and then that is going to be the end of this unit, and we'll do some reviewing, getting us ready for the test we have next time. So remember, in case you weren't here, just want to make sure that we know this. Okay, we have something called the counting principle. We've encountered it a couple times. Remember, the counting principle says this: if you can do a first event in m ways, and then you can do a second event in n ways, then the number of ways you can do them together is by multiplying. It's the whole basis for permutations and combinations. We talked about it at the top of class. So this is the number of ways the two events can happen together. If you remember last time, or when you watched the video from the last section, we used the counting principle to come up with how many codes can I make for my iPhone, how many passwords can I make for a website, just to get an idea of the scope. And the reason I bring it up is because now we're going to combine the idea of how many combinations with the counting principle. So for instance, at a restaurant, ordering a family-style dinner consists of something like this. So if you ever go to someplace like Maggiano's, my dad likes Italian food, so we go there sometimes, and you order family-style, you can select, and I've made up these numbers, but you can select 3 out of 5 appetizers. Okay. You can do 4 out of 7 main dishes, and then you can do 2 out of 6 desserts. So there's 3 categories of things that I'm choosing from. I got 3 different lists. I want to know how many different dinner combinations are there. So what I need to do then, since I have 3 distinct categories, I have to consider each separately. So what I'm going to do is I'm going to apply the counting principle. I'm going to say, okay, the number of appetizers times, so we're going to calculate the number of ways to pick appetizers. Then we're going to multiply that by the number of main dishes times. And then lastly, we're going to figure out how do we calculate the number of desserts. Only this time, instead of like when we did the example of how many ways to flip a coin and then roll a die, and we said, oh, there's 2 ways to flip a coin and there's 6 outcomes when you roll a die. So 2 times 6 is 12. Instead of being given the number, we are told it's a combination problem. There are 3 out of 5 appetizers, 4 out of 7 main dishes, and 2 out of 6 desserts. So it's just a way to get to apply the combination problem a little more. So the number of ways I can pick appetizers is, it's the number of combinations, and I've got 5 objects, and I'm choosing 3 of them. And then my main dishes, okay, it's a combination problem, and I've got 7 objects, and I'm choosing 4 of them. And then last but not least, my desserts, it's a combination problem, and I've got 6 objects, and I'm choosing 2 of them. Once we get those numbers, yes. So we're going to do these separately. I'm going to take a shortcut. Just let's use your calculator here. So what do you get on your calculator, or when you do it out by hand, when you do the number of combinations of 5 objects and you're choosing 3 of them? That's what? That's 10. Okay. So there's 10 ways to pick appetizers. Great. Main dishes. How many different ways are there when you have 7 objects and you're picking 4? What do you end up with there? 35. So there's 35 ways to pick main dishes. And then, last but not least, 6, I'm choosing 2. What'd you say? 15? Great. And so now I multiply those together, just the counting principle. The number of ways to do the first thing, picking appetizers, times the number of ways to do the second thing, pick main dishes, times the number of ways to do the third thing, pick desserts, and that ends up being how many? Right. And there you go. So again, just a couple of other simple made up examples. Remember, simple doesn't mean easy. Simple means less complicated than it could be. So I'm going to give you a couple minutes to set up example 5 and do as much of the calculating as you can. If you need me, raise your hand. I'll come around. Happy to. All right, so I'm just going to get started. If you're working, keep working. So you're taking an English test. You've got to write an essay for 3 of the 5 questions in part 1. And I hated writing essays, and 4 of the 8 in part 2. And you can do this in any order. So how many different ways can you complete this test? Okay, so again, I'm just writing out the steps here. It's the number of ways that we can do part 1, and then times the number of ways for part 2. And again, just like the previous problem, that number is not given to us directly. We have to calculate it as the number of combinations. So for part 1, I've got the number of combinations. I've got 5 objects. I'm choosing 3. In this case, the objects are essays. And in the second one, I've got the number of combinations of 8, and I'm choosing 4. I have room here, so I'm going to write out the next part just so that I don't leave anyone confused. So this, the number of combinations of 5 when I'm choosing 3 is 5 factorial divided by the 5 minus 3. That's the number of objects I'm not using. And then divided by the duplicates. And then the next one, 8 factorial divided by, these are the ones I'm not using. And then divided by the duplicates. Either way, your calculator can do this. So what's the number of ways to choose 3 out of 5? What did that come out to? 10? Yeah, I think we saw that in the last problem. And then what's the number of ways to choose 4 out of 8? 70. And so then that turns out to be, there are 700 different ways you can complete that exam. All right, one more problem. And then if you got any questions, please be sure, get involved, ask whatever you need. So finish up our talk about combinations with example 6, please. Yes, you will get a big number on this one because we got, the more objects you have to choose from, the bigger these things get. That's why in most of the problems, I keep the numbers small. So yeah, so I don't want to, I'm not trying to terrorize anybody, but yeah, you're right. All right, so we've got 15 cats, we've got 12 dogs. We want to make a newsletter. Again, there's no indication that order is important to us in how we're doing any of this. So this is going to be the number of ways to pick the cats times the number of ways to pick the dogs. And that's what we're going to do. And so for my cats, it's a combination problem, and I've got 15 cats, and I'm choosing 6 of them. And then the dogs, I've got 12 dogs, and I'm choosing 4 of them. Again, I'm practicing the formula. So for the cats, I've got 15 factorial if I was using all of them and order was important to me. But I'm not using all 15. I'm leaving off 9 of them. And then I got to get rid of the duplicates because I really don't care what order I put the cats in the newsletter. And then the same thing with the dogs. And then you go to your calculator at this point, and 15, when I have 15 objects, I'm choosing 6 of them. How many ways can that be done? 5,005, so lots of ways. And then 12 objects, I'm choosing 4. How many ways can that be done? 495. And then when I multiply those two things together, it's going to be a large number. What is it? Sound good to everybody? Sounds great to me. Love it.